Okay, today's lecture is pertaining to the completeness of a metric space. So let us take an exercise. Suppose we have a non-empty set, that is x equal to set of natural numbers, and let us define a metric on this, and metric goes like this. We will show that, suppose x is this and let x is this, show that xd is complete. Complete means we have to take an arbitrary sequence from this, which must be Cauchy, and we have to show that that converges in this space. That means complete, right? So in solution we will write down, let's take any Cauchy sequence from this space. So I can write here, let xn be a Cauchy sequence in X. That means any arbitrary Cauchy sequence I have taken from this X, that means set of natural numbers with this metric. So if this is a Cauchy sequence, then by definition of Cauchy sequence, for all epsilon positive, there exists some n naught such that distance from xm comma xn equal to xm minus xn must be less than epsilon. This should happen for all epsilon positive. Since these terms are going to be the natural numbers, and if we introspect on this, so we will come up with a conclusion that difference between two natural numbers is a natural number, or more precisely we can say that there is a whole number. There is always going to be greater or equal to 0, because if this is equal to this, it will turn out to be 0. So that means, since this inequality should hold for all epsilon positive, that means if we set epsilon to be, if epsilon is less than 1, this inequality, this strict inequality should hold. Good. And this is possible for n comma m greater or equal to n naught. If epsilon is less than this, if epsilon is less than 1, then this should be less than epsilon equal to 1. But when this is possible, when this strict inequality is possible, that means this is possible if these terms are going to coincide after some stage. Then this is possible, because otherwise this is not possible, because if we are going to take these two different numbers, for example, if this is 10 and this is 11, then difference is 1, and 1 is not going to be less than 1. That means after some stage all the distances should be less than 1. That is possible if and only if these terms are going to coincide after some stage, because if they are going to coincide, distance will turn out to be 1, and distance is always going to be less than 1, because distance in that case, if we are going to take this equal to this, in that case distance between this and this will be 0. When this is 0 and 0 is less than every epsilon positive, so we can say that if this is a Cauchy sequence, then after some stage all the terms of this sequence are going to coincide. There are more precisely we can say that this is eventually a constant sequence, a kind of. That means after some stage That stage in this case is n naught. After some stage, all the terms are going to coincide. Then this trigonometry is possible. That means, or we can say that this is eventually eventually constant sequence. That is eventually a constant sequence. That is x1, x2, so on, xn naught. After that it will be xn naught plus 1. फिर से आएगा xn naught plus 1, xn naught plus 1, and comma, so on. That means after this stage all the terms are equal. That then we can say that this sequence is Cauchy sequence in this metric. So we have also observed from this Cauchy sequence that this sequence converges to, since we know that this is a Cauchy sequence, and after introspecting on this we observed that this sequence is of this kind. That means after this stage all the terms are going to coincide. We can say that this sequence or limit n approach to infinity, xn is equal to xn naught plus 1, and this belongs to n means x. That means this Cauchy sequence converges to a number, and that number belongs to given space. So we can say that this arbitrary sequence which is Cauchy, converges to a number which belongs to this. So we can say that this metric space is complete with respect to this metric. Okay, thank you.